My name is Mellor Crummey. I'm a professor in computer science at Rice University. Today I'm going to tell you a little bit about the OpenMP Tools API. This is about a 16-month effort, and in part I think the schedule's been dragged out because some of us have day jobs as well. So this is the product of the OpenMP Tools Subcommittee. So the executive lead on this is Martin Schultz at Lawrence Livermore, and the two technical leads have been myself and Alex Eichenberger at IBM, and then as you see there's a long list of active people on the subcommittee who've contributed a lot to the draft that we have presently. So let me start with some of the motivation. So there's a large gap between the OpenMP expression in a source program and the implementation. And so in particular, if you try and drop a profiler on top of an OpenMP implementation, then what you'll see if you don't take any special measures is that you'll see this implementation level view. And so what this is showing is a calling context profile of code that's been compiled and run with OpenMP. And so what we see here highlighted in red is that there's a whole bunch of functions that have been outlined. And so this was done in the context of the Intel OpenMP compiler and runtime. And so there's some calls to launch worker, launch thread, and then invoke func, and then all of these calls to things that have been outlined from the application. And so the problem is that as a tool developer, you lose focus on how all of this stuff fits into the larger whole. And so you need tools to bridge the gap to explain program performance. And I would argue that in this form, it's really not very easy to digest. So the fundamental problem is that the calling context is distributed across threads. So in the developer view, you might have these three code regions, code A, B, and C, where they can be, you can think of them as just pieces of code, and there's function calls and whatnot. And then there's parallel regions that separate them. And so you might begin in thread 1 executing functions in the region code A, and then enter a parallel region B, and then on the same thread, now you can start executing a piece of code B, and then on thread 2, it's a worker that's idle, and so it sees that the parallel region has been entered, and it's a member of the team, so it starts executing code from region B. Then it encounters the parallel region C, and so we end up with some frames on the stack from the runtime system, and then eventually a task gets dispatched for region C. And so there's a big gap between the developer's view, which is shown on the top, and the implementation view that's shown at the bottom. So there have been a couple of obstacles for runtime-independent tools. While individual vendors have their own solutions, it's been hard to build anything that will work with OpenMP implementations in general. There's no standard API for OpenMP tools, and there have been some prior efforts in this regard. The POMP interface, which was described by Moore, Maloney, Shendy, and Wolf, and the collector API by Marty Iskaritz, Mazarov, Kopty, and Lin. And so the problem with both of these is that neither of them gained enough traction, and so maybe I'm just naive, but we're trying a third time and see if the third time is going to be the charm. And so part of the problem is that there are differences in OpenMP implementations. Some of them don't have support for static linking. Some of them have an extra monitor thread. Some of them use a cactus stack, and other things as well. And so what we need is some support inside the runtime system that's going to hide some of these differences from tools and just tell the tools what they need to know. So let me tell you a little bit about OMPT, and then I'll finish up with some status and next steps, and then time permitting I can show a little demo of what the tool looks like using the OMPT interface. So the design objectives for the OMPT interface are to enable tools to gather information and associate costs with both the application source code and also with the runtime system. So we want to be able to profile and attribute costs to the runtime system as well. So it's not just useful for application developers, but it's also useful for all the guys sitting here at the table who might be working on the implementation of these things as well. And so what we want to support is low overhead tools based on asynchronous sampling. We want to be able to identify which frames belong to the application code, which frames belong to the runtime system. And it's not as simple as just saying which frames are in the runtime system shared library. So the runtime system might call C library functions, and what we want to know is which when the C library functions are called, which calls are on behalf of the runtime system and which calls are on behalf of the application. So we want to be able to identify what represents application work and what represents runtime effort. We also want to associate a thread's activity at any point with some sort of descriptive state, like to say it's executing parallel work, or it's idle, or waiting for a lock. So this is individual threads. And we want negligible overhead if the interface is not in use. So for it to be acceptable as something that people will put in their production runtime, the overhead has to be very low if the support is there, but it's turned off because no tool is attached. So our goal is 0, and we'll see how close we get.
0 overhead.
Well, it's not going to be 0,
right.
But it's going to be, we hope that rounding down, it's going to be close. Okay. And so also we're defining support for trace-based performance tools. Now the tracing-based tools are not really my thing, but we felt that it was important to include this as well so that it's a standard that represents the entire tools community. Adding support for tracing inside the runtime, even just the hooks, can add some additional overhead, and so we'll have to see how that all plays out as we refine the implementations to try and bring the overhead down to something that everybody's willing to live with all the time. So we also don't want to impose an unreasonable developer burden on either the runtime developers or the tool developers. So these are the design objectives. And then what we focused on in OMPT is to provide a minimal set of functionality. The essential support for sampling-based tools is part of a mandatory core. And we're only supporting tools that are attached at link time or program launch. We felt that while it would be possible to support tools that are dynamically attached, it would add a lot of complexity to it, and we would rather have something that we can succeed and move forward with and maybe augment at a later time than trying to design this thing in its full glory in one go. The other point is that we want to minimize runtime costs, so we want to reduce the cost in the runtime and the tool where possible to encourage integration and optimize runtimes. And one way to do that is to make support for some of the higher overhead features optional. And so there are some callbacks for this, this idea called blame shifting, which came from my research group, which I'll say a bit about. And then also callbacks for the full-featured tracing-based tools are optional as well. So the major functionality in OMPT is to track the state of each thread. So the thread will keep track of whether it's idle or parallel. And then tools can query this state at any time in using a function that's async signal safe. So in a signal handler, they can query the runtime system and say, what's my thread doing now? And find out that it's doing parallel work or not. And then we also want to provide some limited persistent storage for tool data in the runtime system. And this is something that has kind of fallen on the cutting room floor. And so we'll see whether any of that survives in the final version of the draft. So one of the other things that was important was to support the interpretation of the call stack. So I showed you how complicated the implementation level view looked compared to the application developer's view. And so what we wanted to do in OMPT is provide some hooks that would enable a tool that's using call stack unwinding to identify which frames belong to the application and which frames belong to the runtime system. And then the third part is event notification. So we're providing support for callbacks for predefined events. So a tool can register to receive callbacks when you're entering a parallel region or exiting a parallel region or entering a barrier or exiting a barrier, things like that. So there are a few notifications that are mandatory that we believe that any tool will need, and so they're going to be required in the OMPT specification. And then there are many optional ones that correspond to, say, the blame shifting notifications or the tracing-based notifications, which a vendor could include or not include based on the level of effort and based on the level of overhead that they believe that it would require inside their runtime system implementation. So for runtime state tracking, each thread is keeping track of its own state, and it supports this OMPT get state API. And the idea is you can query to find out what the state is. And if the state is a wait state, like I'm waiting for a lock or a critical region, then the function will return a wait ID, and that will identify in some way, will identify the thing that I'm waiting for, whether it's a critical region or a lock or an ordered section or several other things. So the runtime states, we have states that represent work, idleness, barriers, task waits, mutual exclusion, some miscellaneous things that I'm not going to mention, and then the ones that are in pink color are optional that wouldn't need to be supported. The other ones, while they're mandatory, some of them are actually rather flexible, so you don't necessarily have to report that you're waiting for a lock as soon as there's a call to acquire a lock. In fact, you can report I'm waiting for a lock only after I actually begin to spin wait, or only after I spin wait for some certain amount of time and I fall into a second part of the protocol. So the idea is that we don't want to be too prescriptive to say this is how you have to implement it. We just say if you're waiting for substantial amounts of time, we'd like a notification because the tool would like to know that you're waiting for something. So then there are these three kinds of notifications. So there are mandatory notifications, and then notifications for blame shifting and for the tracing. So the mandatory notifications fall into a couple of classes. So when a thread, a worker thread, gets created or destroyed, we want to know. When a parallel region gets created or destroyed, we want to know. Tasks, if you switch to execute a task, then there's a task switch event. There's also supposed to be a create and exit event for tasks as well. There's a singleton event when the runtime is shut down, and then there's also an event that supports a user level, application level tool control where you can specify that you want to turn the tool on or off, and that's required in the implementation as well. So for the blame shifting events, which are optional, so the idea is these are supporting sampling-based performance tools, and what we want to know is when you're waiting. And so the idea behind this blame shifting concept is that you might be waiting for a lock, and so if I'm using profiling and I'm measuring that a thread is spinning waiting for a lock, that's measuring a symptom. And what we actually want to do is report what the cause is. So we have a strategy where if a thread acquires a lock, so let's say we have time flowing from left to right, so the thread begins and the bottom thread acquires a lock, and then the top thread tries to acquire the lock but ends up waiting for it because it can't. And so then when the bottom thread releases the lock, what we're going to do is we're going to accumulate the lock waiting time in a hash table in our tool, and then when the release occurs, we want to be able to charge the lock holder for all of the waiting that occurred because he was holding the lock. And so that's this notion of blame shifting. It works in a couple of different ways. There's something called directed blame shifting, where you can charge a specific thing, like I want to charge the lock holder, or I want to charge the critical section holder. In other cases, you might be just waiting for work, and what you want to do is say, well, I don't know why I'm waiting for work, but if any threads are running, then I'd actually like to charge them and say that they're not shedding enough work to keep me busy. So whatever code that they're running right now is insufficiently parallel to keep me busy. So that's another kind of blame shifting that's supported by the interface that I mentioned. So this shows up in our tool. I have an example here that may be a little bit small to read on the screen, but what it shows is there's a master region, and inside the master region it's setting a lock and then performing a very long operation, and then all of the other threads are falling past the master region and going into a loop, and then inside the loop you're trying to acquire a lock, and there's a short operation. Now this is not a good parallel program, but this is just, it's a one slide thing that illustrates the point. So it turns out that all of the waiting occurs where the red arrow is pointing, and so all of the threads are waiting for the lock inside that loop. However, all of the waiting is being caused by the activity of the master. And so with this blame shifting concept, we can tell you where the waiting is occurring, and we can tell you who's responsible. So there's a large set of tracing events, and it's for just about everything you would think. For every OpenMP construct, there's either like a singleton event, or there's a begin-end pair, and I won't go through these in detail. For parallel regions and tasks, there are identifiers that are being maintained by the runtime system so that we can collect data and associate it with a parallel region or associate it with a task. And so there's a notion of ancestor levels. So there's the current task, and then I can by asking at ancestor level 1, I can find the parent of the current task, and at ancestor level 2, find the grandparent of the current task. And the same thing for nested parallel regions. I can walk from an inner region all the way through the outer regions. And so this is something that's going to enable us to connect up things that we're gathering from these call stack traces that are distributed across several stacks. So the way the call stack is interpreted, so this is the same example as before, and now we have these little frame gadgets that we're maintaining inside the runtime system that tell you there's pointers that say when we've re-entered the runtime. So next to thread 1, you see where we're entering the frames, the dark gray frames that represent the runtime system code. There's a re-enter that points to the top frame where we enter into the runtime system. And then there's another record below it that is associated with the next task that says, here's where we exited the runtime system in frame 4. And so what we're having is these pairs which really end up marking out like the begin and end of user code, and the things that are in the gaps are the runtime system code. And so with these fingers that are pointing into the stack, and it's just as easy as inside the runtime system just gathering the frame pointer and sticking it into a variable, that we can now stitch together a view of the call stacks that doesn't contain all of the runtime frames in between. So what you see is the application level view. So there are a couple of tool-facing API functions, one for initializing a tool. So the idea is that there's a call that would be made from the OpenMP runtime system to OMPT initialize. And so if it returns 0, that means there's not a tool attached. So the OpenMP runtime system would have an implementation of its own as like a weak symbol. And then if there's a tool that's attached, it supplies a version that will then actually perform initialization and indicate so to the runtime system. There's something for enumerating states, and then something for tool control to turn the tool on and off. Okay, so the status and next steps. At this point, the subcommittee has approved the document that we've been working on for the last 16 months or so. And there were a few late text changes that got committed today based on some feedback from someone on the committee. So the document is available for comment. There's a bit.ly address on here, and if you don't copy it down from the slides, I'd be happy to give it to you afterwards. In the November 7th ARB meeting, the tools group was approved as a subcommittee of the language committee. And the point here is that we don't want a separate tool standard. We don't want a language standard and a tool standard. What we want is a few tool hooks as part of the language runtime system, and so the appropriate thing is for the tools to be part of the language committee. So we're getting ready to submit the TR to the language committee for official comment, and then I hope to turn it shortly into an official OpenMP TR. So right now, IBM has an implementation of the OMPT interface, at least what it was 3 months ago. We've been tinkering with a couple of things, and that's in place on BlueGeneQ and Power. And then my group at Rice and the University of Oregon have been building an implementation into the open sourced Intel runtime. And so I'd say that that's still in prototype form because we think that we can do some things to lower the overhead, and there are also a couple of missing features for some of the corner cases that we still need to add. And so at present, my own group's HPC Toolkit tools are on top of this. It's not our trunk release, it's in the development branch because we've still been changing things on both sides of the interface. So what we have is an implementation of the tool support in the interface, an implementation in a tool, and we've been using the tool on applications. What we wanted to make sure is that when we have something to forward to the language committee, we want to say we know that this is what we want because we've built it and it works. Okay, so if I have just a minute. Go ahead. Okay, I can show you briefly what this looks like inside our tool. So this is, this represents a profile on 24 threads of a shock hydrodynamics code from Lawrence Livermore called LULESH. And what we get with the OMPT interfaces, we've taken the profiles from all of the worker threads and we've knit everything together into a global view. And so I can look down the call paths and it can show me that main inside the function, so there's the function main, inside main there's a loop, inside the loop, there's a call to Lagrange leapfrog. I can get to the code, so I can look all the way down the call stack. So the important thing is what happens with OpenMP. Well, so here is a case on line 1291. It maps to this calc FB hourglass force for elem. So right now the mapping isn't exactly what we'd like, so it's an outline function, and at the moment the outline function is being reported with the same name as the enclosing function. I think we can do a little bit better based on some information that's available in the symbol table. And so what we're able to do is we're able to map back and see that 11.1% of the execution time is inside this function, inside this outline code that's at this particular line in the implementation. And also we can look and see how much time is spent in the fork barrier, which is a detail down inside the implementation of the Intel runtime. So we have two ways of doing this. One is we could just suppress all of the details of the runtime system and just say it was in the OpenMP runtime system. What we've chosen to do is for all of the frames that are kind of along the way, along the path through the middle of the user code, we splice those out. But if we actually took samples in runtime code, then we reported them as part of the full call chain. So we get to see all of the samples that were taken in the user code and all of the samples that were taken in the runtime. So what I can say here is that 6% of the time was spent in the barrier at this statement associated with this parallel region. So one more thing, we also have these upward-looking views. So I can see that 39.9% of this run was in wait sleep. And I can look up and find out that wait sleep was called from hyperbarrier release, which was called from fork barrier. And now I can see for the 32.8% of the time in the execution that was spent in fork barrier, how much maps to every parallel region. So I can see precisely what my overhead is associated with each of the parallel regions. So hopefully what I've shown you here shows that this high-level application-level view is really something that's worth having. And I think that we can actually carry this out with pretty low overhead with the OMPT API. And so it's just a matter of tuning in the Intel implementation. Alex Eichenberger's done some performance studies inside the IBM implementation, and I believe his number said it was less than 1%. I'd be happy to take any questions, or we can all head for a beer.
Any questions? Sounds pretty exciting. Yeah, absolutely. Thank you. Thank you, John.